Okay, so last time we were studying the group of motions of Rn, group G of motions M from Rn to Rn, which preserve the distance function, d from v to w, which is absolute value of v minus w, such that all set theoretic maps from Rn to Rn, which preserve the distance between the 2 points. So this should be equal to d of mv mw. And we had observed that there's a subgroup of this, isomorphic to Rn itself, under addition, of translations. And those are things, if you have a vector b in Rn, and you just take an arbitrary vector v to v plus b. So that translates vectors. And that clearly preserves the distance, because the distance only depends on the difference between two vectors, so the difference is the same if you translate. Now, I claim that G is any element in G can be written uniquely as a translation, an element in this subgroup, times an element in the subgroup I'll call G0, where these are the motions that preserve the origin. And that's clear, because if I have an arbitrary transformation, then it takes the origin somewhere, i.e. m of proof, m of 0 is equal to some b. So if I just compose m with with the translation, let's see, m composed with a translation, let's call this translation t sub b or something. T sub minus b of m of 0 is now equal to 0. So this is an element in G sub 0, and it's a translation times m. So multiplying by t sub b inverse, I get m as get the arbitrary element as a translation times something in G0. And these two groups have no intersection, because no translation preserves 0. So everything is uniquely written as something, it's a translation, something fixing 0. And the last time I claimed was that G0 was isomorphic to On, is the group of orthogonal transformations. Clearly, this is contained in G0, because these are linear maps, so they preserve 0. They preserve the inner product, so they preserve the distance. Right? Because this is just the inner product of v minus w with v minus w, the square root of it. So anything that preserves the inner product preserves the distance. And so this is certainly contained in G0, and the trick is to show it's all of G0. And the trick, last time I showed that if it preserved the distance, it also preserves the inner product. But we don't know that it's linear. I have to prove to you that it's linear. So I'm now going to prove that this is an isomorphism in the following way. Take an element in G0. So m in G0. The claim is that m of v, m of w is equal to vw. This is what we proved last time. It preserves the inner product. And the reason is because you have the formula that d of vw squared is equal to d of v0 squared plus d of w0 squared minus 2 times the inner product. If you expand this out, you get vv plus ww minus 2vw. And vv is the distance from v to 0 squared, and ww is the distance from w to 0 squared. So if you have a group of motions that preserves the origin, it preserves the distance between 2 points. Since it preserves the origin, it preserves the distance of a vector from the origin. It preserves the distance of w from the origin. So it has to preserve this inner product. So anything in this subgroup preserves the inner product. Now consider what it does to an orthonormal basis. Let E1 through En be the standard basis of Rn. Did we ever get chalk? There it is. Okay. Now this has the property that if you take the inner products of the basis vectors with themselves, you get 1. and you take the inner product of the basis vectors with another basis vector, you get 0. Then m of E1, m of E2, m of En is another orthonormal basis. Right? Because this transformation m, which is in Z0, preserves the inner product. And therefore, the lengths of these vectors are 1, and they're orthogonal to each other. Now, consider the following orthogonal transformation. Let A be the element in On with column vectors m of E1, m of E2, m of En. That's an orthogonal transformation because these column vectors are, we know, orthonormal. And the fact that the column vectors are orthonormal is exactly the statement that A transpose times A is the identity matrix. And that's what it means to be an orthogonal transformation. So once I have a collection of an orthonormal basis, and I make the transformation that takes this basis to this basis, that's an orthogonal transformation. Sure?
Just so that I have it straight, what you're proving here is that G sub naught is isomorphic.
I'm showing that any element in G sub 0 is given by an orthogonal transformation. So I started with an element in G sub 0. I proved that it preserves the inner product. I apply that element to my standard basis. I get a new orthonormal basis. And now I write down a matrix that takes this basis to this basis. That's an orthogonal transformation. The claim is M is equal to A as a transformation of Rn. Namely, all I've done is constructed an element in the orthogonal group that does the same thing as M to these n different vectors. And now I'm going to show it does the same thing as M to every vector. Okay? That's what I'm going to try to prove. Proof. What is M of V? Well, M of V is some vector that looks like V1. Let's call it, W1. Has n coordinates, Wn. And V is the vector V1 through Vn. Okay? What are the coordinates of M of V? Well, the way you calculate the coordinates of M of V is that the Wi is the inner product of M of V with the standard basis vector Ei. Okay? Now, I'm going to do it slightly differently. Erase this for a second, but same thing. Consider, to show that M is equal to A, consider the motion M composed with A inverse. Call that motion M prime. That's a motion of space, preserves distance because M was assumed to preserve distance, wherever it was. It's in G0. And A is an orthogonal transformation which we know preserves distance. So this thing preserves distance. This is in G0. And it has the property that M prime of EI is equal to EI for all I. And I want to show M prime of V is equal to V for all V in Rn, i.e. A is equal to M on Rn as a transformation. So I know I've constructed an orthogonal matrix such that when I multiply by its inverse on my transformation, I have a transformation that fixes every element of my orthonormal basis. I want to show it fixes every vector. That's the trick. Well, what is the coordinates of M prime of V? The ith coordinate of M prime of V is the inner product of M prime of V with the ith basis vector. Now, since m prime of ei is ei, this is the same thing as the inner product of m prime with v with m prime of ei. And since m prime is a motion that fixes the origin, this is the same as the inner product of v with ei. And this is the ith coordinate of v. So the ith coordinate of m prime of v is the same as the ith coordinate of v. Which means that m prime fixes v. Yeah. Where I went?
No, the last equals you just wrote.
This one here.
Yes. Okay.
So I have a vector v. I'm trying to prove it's fixed by m prime. So it suffices to prove that every component of m prime of v is the same as the component of v. So here's the ith component is this. Now since m fixes ei, m prime fixes ei, I can replace it by this. Now I use the fact that m prime is a motion, which preserves the origin, so it preserves the inner product. It's this, which is vi, which is the ith coordinate of v. So that shows that m prime of v is equal to v. So let's go over how clever this is. We're given an arbitrary motion that fixes the origin. We construct an orthogonal transformation by matrix that has the same effect on an orthonormal basis, but we don't know it has the same effect on every vector. And then we show it has the same effect on every vector by recovering the coordinates of the vector via the inner product with our orthogonal basis. Very clever proof. So we now have a complete description of the group of motions. The group of motions now looks like this. And let's write down what the product is, too, because now that we know the elements in it, the elements in G0 we've now identified bijectively with the orthogonal transformations. For every m, we've associated a matrix A, so this is ON. An element m of v, where if we have the pair here, we have a B, a translation, and an orthogonal matrix A. What m does to v is it takes it to A of v, the orthogonal transformation plus b. That's the only way you can get a transformation of n-dimensional space that preserves the distance. Slightly more general than the orthogonal group. And what happens if we take the product of BA with B prime A prime? What does that product look like in this group? Well, if we apply it to a vector v, this is BA applied to the vector A prime of v plus b prime. Because that's what this does to the vector v. And now let's figure out what this does. First we apply the orthogonal transformation to this vector. That becomes A of A prime of v plus b prime. This is a new vector. We apply the orthogonal transformation to it. And then we translate by b. And if we gathered up terms, we find the product of AA prime as an element in the orthogonal group applied to v, plus translation by the vector A of b prime plus b. And so if I wanted to write down the product law of this times this in the group, it would equal the element b plus A of b prime A prime. That's what this product of these elements is in this group of motions. It's not a product group. If it were a product group, I'd have AA prime, B plus B prime. It's not quite a product group. So these things don't commute with each other. But note that I do get a homomorphism to the orthogonal group. Namely, if I now consider the map that takes me from a motion, and it just remembers the orthogonal transformation, that takes a pair, BA, to just the orthogonal transformation A, is a surjective group homomorphism with kernel Rn. Namely, kernel is the elements, all of the things of the form B times the identity matrix. Because when I take the product of two elements here, and I just remember their orthogonal component, it's the product of the two matrices. So that part is a homomorphism. And the kernel of that homomorphism is all the transformations that go to the identity matrix here. So those are just the translations. These have the property that when you act on B, you just get B plus B. This is what we call T sub B. So the group is put together out of two groups. Two subgroups. One is a normal subgroup. So this is a normal subgroup. And the other subgroup, ON, is isomorphic to the quotient group via this homomorphism. So now, the rest of the lecture is going to be on the situation when n is equal to 2. Because that's an incredibly rich situation. We're going to spend the next 2 lectures just looking at motions of the plane and what figures they preserve. This is the whole theory of ancient, that was developed in ancient times of symmetry groups. And already for n equal 2, it's a fascinating group, an incredibly rich group. So what we did previously was we worked out what elements in O2 looked like. So for n equal 2, we're talking about the group G, which is R2.O2. So if the translation is trivial, so O2 is G0. And we saw that that was contained a subgroup SO2, which was the rotations around the origin. And then there was a non-trivial coset of that, which I'll call RL, where the elements in this non-trivial coset all had order 2, and they were reflections around a line. Line through the origin. So that if one had a line that was through the origin, you took the perpendicular vector, you got a transformation that was +1 on this line, and where this was an eigenspace with eigenvalue -1, so that the general vector was just reflected around this line. So if you had a vector v, it was taken to the vector, well, over here, the same distance here. This would be v, this would be RL of v, where this was the line L. So for every line through the origin, we had an orthogonal transformation of determinant -1, where the eigenvalues are +1 and -1, -1 on the orthogonal line, and the effect on a general vector is to reflect it across that line. And that was the non-trivial coset, where these were the rotations through the origin, around the origin. So that we did last time. Now we didn't do one thing last time, which we have to do if we really want to understand this group. Namely, this is a commutative group. If you compose rotations, you just add the angle. It doesn't make any difference in what order you multiply. But we want to see what happens when we conjugate a rotation by a reflection. So what is the formula for RL of the rotation through theta composed with RL inverse? Because that'll give us the structure of the multiplication law in this group. We know how to multiply things in here. We have to know how to multiply things if we have something in here too. Okay. Now this turns out to be very simple to work out. By the way, RL inverse is what? RL. Because if you think about this reflection, if you do it twice, you get back to the identity. So this can also be written as RL composed with rotation by theta composed with RL. Now I claim, without doing any thought at all, but we're going to have to do some thought in a moment, that this is the rotation through some other angle, theta prime. And what we have to do is figure out what theta prime is. Now how do I know that whatever this transformation is in O2, it has to be a rotation through an angle theta?
Because it is orientation preserving and it fixes a point.
Yeah, it certainly all these things fix the origin. And the point is that this thing has determinant 1. Because this has determinant -1, this has determinant 1, and this has determinant -1. So the composition has determinant 1. It's a rotation. All we have to do is figure out the angle. Now, to figure out the angle, all we got to do is follow one point under this transformation, right? So here's what we're going to do. Here's our line L. We're going to follow the behavior of a point on L and see where it gets rotated. And once we do that, I know where everything gets rotated. Okay, what happens if I apply this transformation to a point on L? What does the first part of it do? 0. It does nothing. It fixes L. This line is fixed by the reflection. So P stays where it is. So this is equal to sigma L of P, or RL of P, sorry. And then the next thing I do is I rotate it through an angle of theta. And it goes over to rot theta composed with sigma RL of P. And then the final thing I have to do is the reflection around the line L. Here's the final point. RL of rot theta composed with RL of P. Namely, I take it to the other side of L. What's this angle here? Negative theta, exactly. So what I've done is I've taken P and I've rotated it by minus theta. So that's the formula. And this rotation, by the way, is the same thing as rotation of theta inverse. Because if you wanted to invert the rotation of theta, you'd rotate back by minus theta. So in particular, this is a very cool group. This is a commutative group. And anything in this coset, because anything in this coset is some RL, has the fact that when you conjugate, this is a normal subgroup. And if you have anything in this group, H, and you conjugate it by anything outside it, you get this identity. So it's not a commutative group, because R doesn't commute with H, but it takes H to H inverse. For any element in H in here, H in SO2, or an R in SO2 union RL, in the non-trivial coset. Anything in one coset, and you try to commute with anything in the other, you get the inverse. So that's the multiplication law in this group. Good? Very interesting. And all we did to figure that out was, we knew it was a rotation. All we had to figure out was what it did to one point. We conveniently chose the point on the line, so the first transformation did nothing to it. Okay. Those are our descriptions of elements in the group O2, which is what we call G0. But what's amazing is that you get simple descriptions of all elements in G. So that's a big theorem, that any element in G has a simple geometric description. There are 4 basic types. One. Well, remember, we have a map from G to O2, this homomorphism up here. And on O2, we have another homomorphism, the determinant, that takes us to plus or minus 1. So we have a subgroup of G consisting of the elements, when you first map them to O2 and then you take the determinant, are plus 1. Those are called the orientation-preserving elements in G. So we're going to do the determinant of G, if you allow me to say this, is plus 1, orientation-preserving. And then you have the elements determinant of G is minus 1, reversing. Now, we know that any element which is of determinant plus 1 has the form translation by beta composed with rotation theta. But that's a complicated description, because we don't really know what that does to a point. It says, first you rotate it by theta, then you translate by b. What does that really mean? And here we know that everything has the form translation by b composed with rotation by theta composed with reflection in a line L. Because the non-trivial coset is, translations and elements in here. But that's not very useful, because geometrically we don't see what these are doing. It's one of 4 geometric types. So these gives 2 types. One's are just pure translations, and those just are the form TB. So there you just take every point and you translate it by b. That's the simplest case of this where the rotation is trivial. And the second is, so these translations fix no points, or all points, if b is equal to 0. If it's the identity element, it fixes every point in R2. But the general translation fixes nothing. And then there are the elements of this form that fix a single point. And consist of rotations around P. That's not obvious from this presentation at all. But we're going to see that anything of this form either is a translation, fixes nothing, or fixes a single point and rotates points around that. Anything of this form is either what's called a reflection. That's where b is equal to 0. So that's of the form reflection of L prime in a line. Or what's called a glide reflection, where you reflect around a line and then you compose that with translation in a vector parallel to the line. So this has the property of fixing everything on the line L, because the reflection fixes everything on the line L. And this has the property that it doesn't fix every vector on the line L, but it fixes the line L. Not pointwise. Because this fixes all the vectors on the line, and then you're translating by something parallel on the line. So the first thing takes your point here, and then you just translate by a vector that's running parallel to L. So the amazing thing about these transformations in this motion group G is they come in 4 types. The things that fix nothing, neither points nor lines. The things that fix a single point. The things that fix points in a line pointwise. Those are the reflections of order 2. And the things that fix a line as a set. Those are the glide reflections. And that's it. Every element, you can either associate to it nothing, it's just a vector, a translation, or you can associate to a point, or you can associate to it a line, or you can associate to a line and a slide vector. So I'm going to prove to you this part. And I'll leave this part for you to look at in the book. Again, the trick is finding the line, finding the point. So let's see if we can do the first half of this. Break up everything in this determinant 1 coset to either a translation or a rotation around some unspecified point. Okay. So if theta is equal to 0, this is where theta is equal to 0, and this is where theta is not equal to 0. All right, so I'm going to show you where the fixed point P is. Theta is not equal to 0, and B is not equal to 0. If B is equal to 0, then P is just the point 0. And we are in Z and in the group that we already know. So assume B is also not equal to 0. Where is the fixed point? So I'll draw you a little picture of how you find the fixed point for this transformation. First you rotate by theta, and then you translate by b. And theta is a non-zero angle, and b is a non-zero vector. Okay, so what you do is you take the vector b. It's non-zero. So therefore, you take the line there's a unique line orthogonal to it. Since it's non-zero, we can find an orthogonal line. And then we take angle theta over 2 to the north of it and theta over 2 to the south, so that we have a sector around this orthogonal line where the angle here is theta. and we're going to rotate theta in this direction. So we're given two things. We're given a vector b and a non-zero angle theta in this transformation, and we're trying to find the fixed point. So I take the line orthogonal to b, I take a sector around it where the total angle is theta. Namely, I take this line of degree theta over 2 over this line, and then theta over 2 below this line. All right, now take this vector b and start moving up in this sector, which gets larger and larger and larger. And by continuity, you eventually come to a point where you have a vector parallel to b. Let's see if I can even draw it, which starts here and ends there. Let's parallel to b. Does that look parallel? Close enough. There's a unique point in this sector where the vector b goes from, where a vector parallel to b goes from here to here. Right? Because this sector is by continuity getting larger, and eventually it's separated by, you're taking vectors perpendicular to this line because they're parallel to b. So you start off with short vectors, and they're getting longer and longer and longer, and eventually you get to a vector of exact length b, and you stop. Okay? The claim is this is the point p. This point is fixed. It's at least one point that we've constructed that's fixed. Let's see why. What's the transformation? The transformation is rotate by theta and then translate by b. When we rotate this point by theta, we go to this point. Correct? Because we've rotated it through an angle of theta. And then when we translate by b, we go right back to this point. T of b. So there's our fixed point. Now I claim that's it. That's it. No more fixed points. Okay? Because once I fix the point in the plane and I have a motion of the plane, it has to fix the points of a fixed distance from that point. Because it preserves now the distance from P to V. And it also preserves the point P. Right? And the only thing that can happen if you have determinant 1 is it just rotates you around each circle by an angle of theta. So I leave the final proof of that to you. If it fixed anything else, then it's too many vectors that are fixed. You know, each vector of a positive distance has to be rotated through a positive angle, because this transformation is not the identity transformation, because both theta and b are non-zero. If either of them is non-zero, it's the non-identity transformation. So finish it by saying that once you have a fixed point p, it preserves the distance from p, and then it preserves orthogonality. So once you know where it takes a vector of distance, so you start with, say, an orthogonal set of vectors coming out of P. It rotates this through some angle theta, just like our previous proof that we identified the transformations that fix the origin. Therefore, it has to take this vector to something of the same length, which is orthogonal to this vector. So there are only two choices. And then you see which one has determinant 1. And it turns out to be a rotation. So the book will show you, if you're given a transformation like this, how you find the line that it fixes pointwise, that it fixes as a line. And I'll leave that. But this is some amusing geometric constructions to show that any transformation either fixes a point or fixes nothing or has a line that is stable. Okay. Now with this knowledge of individual elements, we're going to go back to the group as a whole. Individual elements are all very nice. And what this is saying, that any one element in G, you can sort of understand the geometry of it. Of course, composing elements in G becomes quite complicated. If you have an element that fixes a point P, and you have an element that fixes another point Q, and you compose those, right, that's going to fix another point, depending on P and Q, because it's going to be in this subgroup. But which point it is, etc., it gets quite complicated. So we're going to go back to study now the group as a whole, and we're going to study first the finite subgroups of it. So a finite subgroup I'm going to call gamma. This is, of course, an infinite group. In fact, if I have a translation in my subgroup, it's not of finite order. Because if I just keep doing a translation, I keep translating out and out and out and out and out, and I never get back to where I started. So this has no translations in it. Finite subgroup contains no translations. It can certainly contain rotations around a point, and it can certainly contain reflections, because we've seen in the case of just the group fixing the origin, you could rotate a third away around the circle, and if you did that 3 times, you'd be back to the origin. So that would be an element of order 3. Or the reflections give you elements of finite order. So there are all kinds of possibilities for finite subgroups. And the first theorem is, and this is very useful, any finite gamma fixes a point P in R2. Namely, not just each element fixes a point, but the theorem is that there is a point that's fixed by every element in the group, i.e., gamma of P is equal to P for all gamma in gamma. So that's the key to the classification of finite subgroups, and then we'll finish it rather quickly once we prove that. So again, if you claim that, just like I claimed that this composition fixed some point, you have to be able to show which point it is. You have to give a recipe for that point P that's fixed. So I'll give you an abstract recipe. It goes like this. Let S be any point. Any vector. And consider the vectors gamma of S, where gamma is in this finite group gamma. So we start with some vector S, and we start applying the group to it. We get some new vectors, gamma squared of S, etc. And that defines a finite set of vectors in the plane, possibly with repeats. Gamma might fix S. We don't really care. So this is a finite set of vectors in R2. Okay? And now, and this is the brilliant idea, you let P be the center of mass of this set. So let N be the number of elements in this set, say N distinct vectors. Well, we'll even do it, say N vectors, possibly with repeats. We don't care. So N is the order of gamma. Let's do it this way. And let P be 1 over N times the sum over gamma in gamma of gamma of S. So this sum means the vector sum. So you sum them up. And then you divide by the real number 1 over N, where N is the number of vectors. So that's like a barycenter or something like that. If you added up, if you had 4 vectors like this, and you added them up and you divided by 4, you'd find the center there. That's P. Okay, the claim is P is fixed. Claim is that P is a fixed point. Well, you see, what happens when you apply gamma to P, an arbitrary element in P? Well, it could be a translation or it could be a linear map. So gamma, remember, is enough to check. So the claim is if G is in G, then this is the general group, then G of P is equal to 1 over N the summation of G of gamma of S. So you translate all the points by G, and you sum them up, and you take their average. That's what you get, G of P, for any G and G, not just gamma. Well, it's enough to check this. Remember, this group was R2.O2. So it's enough to check for translations and rotations. It's clear for rotations because G is a linear map. So when you apply it to a sum of vectors with a constant in front, you just get the sum of the G's. And for a translation, well, you just have to check that if you translate all the points, you've added B n times to this, then you divide by n, so you've added B to this vector, which is exactly what you do if you apply G to P. So if you check it separately for translations and for orthogonal transformations, then it's true for the composite too. So these because they're linear maps, and these because you've divided by n. So the summation of B n times 1 over n is equal to B. That's what you're using. Well, now apply this to G and gamma. If you do that, so we get that gamma of P is, well, let's call it gamma prime, 1 over n, the summation of gamma prime gamma of S. Summation of gamma and gamma. But these elements are just another way of running through the group. Right? If I have a collection of elements in a finite group and I multiply them all to the left by one element in the group, I just get another reordering of the elements in the group. So the elements in this sum are exactly the same as the elements in the original sum, perhaps in a different order. But vector addition is commutative. We don't care what order we add them up. So this is the same thing as 1 over n, summation of gamma of S, which is P. Just rearrange the terms in the sum. And vector addition is commutative. So now you see why we needed a finite group to get a fixed point. This doesn't make any sense if you sum over a general subgroup, because we don't know how to add up an infinite number of vectors. But for a finite group, no matter how large, we can add up those vectors, divide by the number of vectors. That gives us a new vector in the plane, and that's the fixed point. Okay. Now we know the subgroup fixing the origin. If this fixed point is the origin, if P is equal to 0, then gamma is actually a subgroup of what we called O2. In general, gamma is now a subgroup of a conjugate of that. So since gamma fixes a point P, gamma is actually a subgroup of G fixing P inside of G. G of P is equal to P. And I claim that this group is exactly the following group. It's G sub 0 conjugated by T of P inverse T of P. Well, let's check that the elements in this group fix P. If we apply T of P inverse to P, it goes to 0. G0 fixes 0, and then T of P translates it back to P. So these elements certainly fix P. And conversely, if you have an element that fixes P, then conjugating it by T of P takes you to an element that fixes 0. So this conjugate of G0 is exactly G of P. And conversely, if we then conjugated gamma, which doesn't change its structure as a finite group, remember, conjugation is an automorphism of this group. So TP inverse gamma TP is now a subgroup of G0. Call this maybe gamma star or something. So this is a finite group, isomorphic to gamma. And this is the group O2. So what we've proved is that the finite subgroups of this complicated group are isomorphic to the finite subgroups of this rather simple group, O2. That's not going to be true when we try to do what are called discrete subgroups of this motion group. But at least for finite subgroups, we don't really gain any generality by going to the motion group. We might as well just stay inside of the subgroup that fixes the origin, because any finite subgroup fixes a point, and by conjugating, by the translation that takes that point to the origin, we can move the subgroup into the subgroup fixing the origin. And so if we're only interested in the abstract structure of these finite groups, we might as well classify the finite subgroups of O2. Okay, so now that's what I'm going to do. That's how I'm going to finish. I'm going to tell you what are all the finite subgroups of O2. Well, there are really two possibilities. So classify the finite gamma in O2 now. Case 1, gamma might be contained in SO2. Namely, everything in gamma might be a rotation. And case 2 is gamma intersect SO2. Let's call that gamma plus. Has index 2 in gamma and is normal subgroup. So either the group is contained in rotations or its intersection with rotations is a subgroup of index 2. Well, this is the situation where the determinant of everything in gamma is plus 1. And this is the situation where the determinant of everything on gamma is either plus or minus 1. And you have elements of determinant minus 1. And gamma plus is the subgroup where the determinant is plus 1. And so we get this homomorphism, the determinant from gamma to plus or minus 1. And in the first case, it's the trivial homomorphism. And in the second case, it's surjective. And so its kernel is of index 2. So you get some groups in this case, and you get some groups in this case. Let's do this case first. I claim in case 1. So therefore, everything in gamma is every gamma is some rotation in some angle theta, where 0 is less than or equal to theta. It's less than 2 pi. Okay? Now, if we want to classify it, we're going to do the following argument. Let theta be the smallest angle of rotation for any element gamma in gamma where theta is greater than 0. Of course, you have the identity element that rotates through nothing. So we find the smallest angle of rotation. So this is, the vector E1, and this would be gamma E1. There are only a finite number of angles of rotation, so there's a smallest one. Okay? Then the claim is that the element that this is and gamma, then gamma is a cyclic group generated by this element. And if the order of gamma is equal to n, this element theta is 2 pi over n. Okay, well, to prove it's a cyclic group, you just say, well, if I had something else in this, suppose I had some other angle of rotation. I don't know, here it is, theta prime. And what I have to show is that theta prime is some multiple of theta. Well, if it weren't, I'd march up, I'd get a multiple that was less than theta prime, I'd get a multiple that was bigger than theta prime. And by taking this element times this multiple of gamma inverse, I'd find an element that was smaller than theta, which was an angle of rotation in the group. So it's just like proving that subgroups of a cyclic group are cyclic. It's really the Euclidean algorithm disguised as angles. So that proves that any element in the group has to be a multiple of theta, and if you want this element to have order n, you have to have rotated exactly 1 over n around the circle, which means the angle is 2 pi over n. And note that any such cyclic group can occur as a finite group, because I just take this angle, and that gives me an element of finite order n in SO2. And if I take the cyclic group generated by this, I get a finite group, cyclic group of order n. In particular, every subgroup here is cyclic, and all orders occur. So that's a nice way of doing cyclic groups. They're all cyclic groups are subgroups of SO2. Okay, here, let's finish this quickly. In this case, we know that this group is cyclic because it's a finite subgroup of SO2. So this group, gamma plus, is cyclic of order n, some order n. And it has index 2 in gamma, so that gamma has order 2n. And it contains in it, let me call this group Cn, a cyclic group of index 2. Now it also has to contain a reflection, because we said the determinant was -1 on some element. So take an element in gamma which is not in this cyclic group. Call that reflection around the line L. And call that maybe R. Then R squared is equal to 1. And on this cyclic group, we know that R inverse is equal to H inverse. Right? Because that was true for an arbitrary element in SO2, in particular for the elements in the cyclic group. So we see that in the case where this group has index 2, that gamma is generated by two elements. It's generated by a rotation in an angle 2 pi over n, which has order n. And then it's generated by a reflection, R, which has order 2. And this is a normal subgroup, and when you conjugate by R, you get inversion on this subgroup for every element, because that was true in the general O2. And these groups are called dihedral groups of order 2n. And once n is bigger than or equal to 3, they're non-abelian, because not every element is equal to its inverse inside of H. And a typical example of a dihedral group that we've seen before is the symmetric group on 3 letters is isomorphic to the dihedral group of order 6. This group I would call D2n. The book calls it Dn, but I like to keep track of the order. So here, this is the cyclic group of order n, and all cyclic groups occur. Here we get the dihedral group of order 2n, and all dihedral groups of order 2n occur. And those are the finite groups inside of inside of O2. And in particular, any finite subgroup of G is isomorphic either to a cyclic group or a dihedral group. Now, this is the beginning. This is just the beginning. The next thing we're going to do is not classify the finite groups of this motion group, but are what are called the discrete groups. And that's where we get into the beautiful study of symmetry. So make sure you have this down in your head, because finite subgroups turn out to be a subset of the discrete groups. But the discrete groups are going to have things like translations in them. So that's what we're heading for on Friday. Okay.